In the last lecture, we discussed first countable spaces. So they are the topological spaces X, which has a countable basis at point X in X. That means we have a countable collection Bn, which is the sets B1, B2, Bn, and so on at a particular point X, such that each each of these sets is a neighborhood of the point X, and at least one element of this family contains is contained in U, which is a neighborhood of X. So this is basically the property at each point small x belongs to capital X, and therefore this is a local kind of local basis at X. So that is this property is known as first countable spaces. So whatever spaces satisfies this property, we call it first countable topological space. So we have discussed that each metric space X is first countable. So that we have already observed that if we take around in any metric space X, which we take any element small x, and we consider all the open balls around that point with radius 1 upon n for every n, then this family of open sets forms a basis, the local basis. So therefore every metric space is a first countable space, and in particular we have seen that the set of real numbers with the usual metric, that is the standard Euclidean metric, is also metric space, and we verified at x equal to 0, but this holds for every x. So around x we take the neighborhood of radius 1 upon n, that means the open intervals of radius 1 upon n. Then every open set U containing x has at least one basis element in between x and U. So x is contained in that basis element which is contained in U. So that means the set of real numbers is first countable. And then we have seen that the second countable spaces, that is a space capital X has a countable basis if the collection of all basic open sets itself is a countable collection. So the question is, for the set of real numbers with standard topology, can we find a basis which has a countably many basis elements? So this is one such collection that if we take x equal to r, then we can actually find such a basis which are the open intervals having endpoints as rational numbers. So this collection forms a basis. So we have already discussed the proof of this, that if we take if we consider the collection of open intervals with rational endpoints, then it is a basis for a topology on R, and the topology generated by that basis is actually the standard topology. So that also one can check by the standard argument. So we know the topology, once we know basis of two topological spaces, then how to show that the topology generated by that two basis is same or not, that we already discussed. So similar argument we can give in this case. So one part we have already discussed, that one of the topology is stronger than other. The other part is trivial. So uh, so that means the the set of real numbers with the standard topology is a second countable space. So that is what more or less we discuss here, and then we discuss a lemma that every second countable space is first countable. So whenever we have a topological space in which we have a countable basis, then it will always contains countable bases at a particular point. So that is what we discuss in this lemma. After that, we discuss dense subsets. So a subset A of X is dense if its closure is the whole space. And we know the standard example that rationals are dense in real numbers. So when we take the closure of Q with respect to R, then it is closure of Q with respect to the standard topology. Then we get the entire space R. So that is this example, and because the closure of a set depends on which topology we are taking, so therefore that is also important. So after that, we discuss that a topological space X is called separable if there exists a countable dense subset of X. So again, here the example is that R is separable because with respect to standard topology, because Q closure is R, right? So here also the reason is that Q closure is R, where closure we are taking with respect to the standard topology. After that, we discuss one theorem that every second countable topological space X is always separable. So if I have a second countable topological space, that means we have a collection of basic open sets which is countable. Then we can construct a set D so that its closure is X. So I think this is what we discussed in the last lecture up to this point. So today we want to discuss uh, some more uh, types of topological spaces. They are related to Hausdorff spaces. So if you recall the definition of Hausdorff space, then a Hausdorff space is that if we have a topological space X, X is Hausdorff if we have 2 points X and Y, or X1 and X2 in capital X, then we can find two neighborhoods U and V of X and Y, so that this neighborhoods, the intersection of this neighborhood is phi. That means they are the disjoint open side. Right. So such a spaces are known as a Hausdorff space. So here x1 belongs to u1 and x2 belongs to v, u and v. So this property is briefly we can say that u and v basically separate the points x1 and x2, which are the distinct points. X1 is not equal to x2. So they are distinct points. So whenever we have a pair of distinct points x1 and x2, we can separate them by open sets u and v which are disjoint. So in this case, u and v are known as separation of separating x1 and x2. So we will see this terminology briefly. So let us see in the definition. A topological space X is called regular space if it satisfies the following two properties. First property is that the singletons are open. So singleton sets uh, is closed subset of X. So closed with respect to the given topology for every X belongs to X. So this first property says that every singleton is closed in this topological space. And second property is that instead of we can separate two distinct points, now we have uh, two different objects. So for each point x in X and each closed subset B of X, so that X is not in B, there exists disjoint, there exists open subsets U and V of X such that X belongs to U and the closed set B is contained in V. Alright, so let us see by the diagram what does this mean. So this means that whenever we have any element X in this topological space capital X and we have a closed set V, which does not contain X, then we can always find two open sets U and V so that U contains X, V contains B, and the intersection of U and V is null set. Right, so they are disjoint sets basically. So what is the difference between regular space and Hausdorff space? So in regular space we can separate a point and a closed set by open sets U and V, and in the Hausdorff space we can separate the point with the 2 points we can separate instead of point with the closed set. So that is the difference between these definitions. So in this case when we have the separation of X and B, we say that U and V, these two sets separate X and B. So whenever we can find such a sets U and V for X and B, we will say that U and V separate X and B. Right. So this is one of the terminology which we will be using in today lecture. So let us see one simple lemma which says what is the relation with the regular space and the Hausdorff space. So by the definition and the diagram itself, we can easily see that every regular space is always a Hausdorff space. So let us see that in details. Say that if X is a regular topological space, then X is a Hausdorff space. So proof is very simple from the graph that whenever we have a regular space U and V separate X and the set closed set B, and here we have to show that it separate X and Y, right? So uh, just we need to observe that we have to choose a particular set B which contains the Y, right? So to prove X is Hausdorff. We need to find separation U and uh, we need to find open set U and V which separate X and Y, where X and Y are distinct points, right? X is not equal to Y. So this will follow directly by the this will follow directly by the hypothesis by the definition of regularity. A regular space is if we choose particular closed set B, and that will be singleton Y, right? Because what is given is we are given 2 points X and Y which are disjoint which are distinct points, and we need to find open sets UV which contains these 2 points and uh, their they are open sets. So if in this second regularity condition, if I choose this set B itself to be only containing point Y, that means we are in this situation. We have only singleton set, right? So that means the sets U and V which we will get from the regularity property, that will gives us the separation U and V of the point X and Y, and that is exactly what we want for the Hausdorff property. So just this is a kind of showing that the regularity definition is a generalization of the Hausdorff space. Regularity property is stronger than the Hausdorff property, right? The same way we can generalize in the both the sides. So instead of considering a point with the closed set, we can also consider both the side closed sets, right? Instead of choosing a point with the closed set. So that another we will get the definition when we have this property for two closed sets. So such a spaces are known as normal spaces. A topological space X is called normal if in which we have the singleton sets is closed for each X in X, right? And the second property is that for each pair of disjoint so instead of taking for the regular spaces, we have selected one point X with closed set B. So now instead of the point X, we will choose another closed set. So both the object which we will select is are disjoint closed sets. So for disjoint closed set A and B of X, there exist disjoint open sets U and V of X, so that the first set closed set is contained in U and the second closed set is contained in V. So again in this case also we will call U and V separate A and B. Right. So here also the diagram is a bit simple, that whenever we have a topological space X, it is normal if first of all singletons are closed, and whenever we have two closed sets A and B which are disjoint, we can find we can always find two open sets U and V which are disjoint sets, and U contains A and V contains B. Right. So this case we can see that this is a generalization again for the for of uh, this diagram, because again what we will do is we will take A to B singleton X, and then this property will follow uh, from the general property, from the stronger property. Right. So so let us write down that in form of a lemma, that every normal topological space is always regular. And proof is a bit simple, that to prove it is regular we have to since singletons are closed in each of these spaces, regular, normal and Hausdorff, so that property anyway follow, but we need to prove basically the second property, that uh, so whenever we have a point and a closed set, we can separate by U and V. So given X element of X and a closed set B of the normal topological space X, normal topological space X. So now if I want to use the property of normal, I have to choose two closed sets. So one closed set is given B, so uh, denote singleton X, the closed singleton X by A. So now we have two closed sets A and B. So since X is normal, we get open sets U and V by the definition of regular space, such that U and V separates X, A and B. So A is singleton X uh, and the closed set B. Right. So so this means that singleton X is subset of U and V is subset of V. So finally what we get is X belongs to U and B is subset of V, and we also have uh, U and V separates the sets. That means their intersection is null set. So that means we have all the properties satisfied for the regular space, right? So therefore X is a regular, because for every point X and the closed set V does not contain in X, we have a separation. We have the open sets U and V which separates X and B. So this is basically by how we can generalize the definition uh, of the Hausdorff space, and we are getting this. So every regular space is Hausdorff and every normal space is regular. So what is the what is the so that means every normal space is Hausdorff space. So let us write down by a remark that every normal space is Hausdorff. Right. So every normal space is Hausdorff. So what about the converse, that if I were when a Hausdorff space becomes normal? So that is a question. So that result we will discuss now. That so usually compact Hausdorff spaces are very important uh, because we have seen one result regarding the inverse function of uh, when an inverse function become continuous, right? So that result involve compact and Hausdorff both the property. So usually in mathematics, mostly we discuss compact Hausdorff spaces because they have very interesting properties. So one of the such result is this one, that every compact Hausdorff space is always normal. So this remark says that every normal space is Hausdorff, but when a Hausdorff space is normal, so whenever it is compact, it is normal. So let us see how compactness plays role in this proof. So we want to prove that X is normal. That means we will we have to show that each singleton is open. So first thing is each singleton is open because it is a Hausdorff space, right? Because whenever we have a point X, and whenever I take a point Y which is different from X, then I can always have a two open sets, right? So in particular I have, for each Y which is different from X, I have a neighborhood around Y. So that means the complement of singleton X is open, right? So for each Y not equal to X, there exists an open set Uy containing Y which does not contain X. So this follows because X is Hausdorff. Right, so we are using this property that X is Hausdorff. So for every element Y which is different from X, we have a neighborhood around that point. So this will give us that singleton X is the complement of singleton X is an open set. And since the complement of the set is open set, therefore the set itself is a closed set. So this is basically the proof that in a Hausdorff space every singleton set is always closed set, right? So every singleton is closed set in the Hausdorff space. So this is basically the first property of the normal spaces, that a space is normal if the topological space is is normal if each singleton set is closed, and whenever we have a two disjoint closed sets, we can separate them by open sets U and V. So now the second property which we want to prove is that whenever we have a two closed sets X and V, A and B. So let A and B be two disjoint closed subsets of X. So now X is compact Hausdorff space, and we have a closed subset of the compact Hausdorff space. So then that closed subset itself is a compact space, right? So since X is compact space and A and B are closed subsets of the compact space, A and B becomes A and B are itself compact space, right? Each closed subset of a compact space is compact. So A and B are now compact spaces. And then we know that for compact spaces we have, if we have open cover, we can find a finite subcover. So now let us divide uh, this argument into two parts. So first we will choose the set A itself to be singleton set. So now A is a closed subset of X, so it has two cases: either A is singleton set or it is not a singleton set, right? So first we will in the first case we will discuss the simpler case, that is if A is singleton set, right? And in the second case we will discuss that if A is not a singleton set, so that means A contains more than one point. So if A is singleton set, then for each Y belongs to B, because A and B are disjoint sets. So whenever we have a point Y in B, uh, there exist open sets Uy and Vy, so that X belongs to Uy and Y belongs to Vy, such that uh, so not only this holds, we also have uy intersection vy is null set. So this follows because x is Hausdorff. So x is Hausdorff means whenever we have 2 points x and y, we can separate them by open set u and v. So here also we are choosing x and y, but we are changing y basically. We are changing y over the set of all elements of the uh, we are changing y over the set of all elements of capital B. Right. So as many capital B is there, as many we will get uy and vy. So if B is finite, we will get this pair uy vy finitely many. If elements of B are infinitely many, then we will get infinitely many uy and vy. Right. So now what we will have is basically for each y we are getting vy which is open set. So what we'll get is that B is a union of singleton y, and each singleton y is subset of vy. So each singleton y is subset of vy. So therefore union singleton y is subset of union vy. So and therefore we get this collection vy, which is collection of open sets. So this covers is an open cover of B. Cover of B. And what is B? B is a compact space. Right. So B is an open B is an compact space. So now what can we say about uh, using compactness? So compactness says that every open cover contains a finite subcover. Right. So therefore we get a finite subcover so this finite subcover which we are getting is vy1 y2 yn. Right. So this is what uh, we get a subcover of B, and then using this subcover, let u define to be uh, so corresponding to this vy1 vy2 vyn, we will get uy1 uy2 uyn, which is corresponding sorry corresponding sets in terms of u. Right. So using those sets, we will consider uy1 intersection uy2 intersection uyn. Right. So all these sets will take intersection, and for v sets we will take union. Right. So these sets we have union, and the simple observation uh, using set theory will gives us that u intersection v is null set. Right. And moreover if x belongs to u, and if we choose the set, uh, it is easy to see that x belongs to u because x belongs to each of the uy, right? For every y, x belongs to uy. So therefore x belongs to the intersection of uy. So therefore x belongs to u. And on the other hand, y1 belongs to vy1, y2 belongs to vy2. So therefore finally we get the set B itself is contained in V. Right. So in this case, our property of the normal space is satisfied for the case 1 when A is a singleton set. So now we will consider case 2. So case 2 means is not necessarily the singleton sets. So that means if A is any arbitrary complex size. So if A is arbitrary compact space. So in this case, what we will do? So here also we are going to use the similar argument. So if A is any arbitrary complex set, then for each x in A we can find open set ux containing x and vx containing b. So instead of uh, so here what we have done is we have selected for each x and b, we have selected uh, the cup open cover, right? So in case 1, what we have proved basically is that whenever we have a singleton set X and whenever we have a closed set B, then we can separate them by open sets. So now we are using case 1. So using case 1, what we will get is then using case 1 for each X element of A and the closed set B, we get UX and VX, UX and VX, which separates x and y, x and b, right? So now we get a for every x we are getting such a pair u of u and v, so that x belongs to ux and v is a subset of vx. So this will give us that, therefore we get uh, an open cover which is ux, so that x belongs to a. So this is open cover of a, and a is compact. So since a is compact and this is open cover, so therefore we get a finite subcover, say ux1, ux2 up to uxn of a. So basically in this case also what we'll get is we get two open sets where u is ux1 union ux2 union uxn, and what is v is is intersection of this Vx1 intersection Vx2 intersection Vxn. So each Vxn contains B. So therefore, what we get is A is a subset of U and B is a subset of P. Right, and in fact they are disjoint. So this is basically the proof of this result that every compact Hausdorff space is a normal space. So I think this would be enough for today lecture. So let me stop the recording.